This is part B of the lesson on solving systems of equations, taken from Chapter 8, McGraw-Hill Ryerson's Pre-Calculus 11. The outcomes, or the lesson objectives, we've covered some of these already, but we're looking more at interpreting our points of intersection and solve a problem that involves a system of equations. So looking specifically at 4 and 5 in part B. So to begin, just a reminder that as you're watching this video that you pause, do the questions, then pop right back into the play so you can get the answers so that you're participating in the video. So we have this question. This is our example 4. Students were given the following system of equations. So we were given this system. We were asked the following questions. Well, I shouldn't say. Okay, so Lynn stated that the solution to the system was -4, -1. So this is what she had told us as our answer. And we want to verify that that point is a solution to the system. We are asking, is this the only solution to the system? And to justify our reasoning, so explain why it is, why it's not. When there is a quadratic-quadratic system, what are the possible types of solutions that we can see? So we've got a couple of guiding questions. Let's look at the first one. The first one's asking us to verify. So this is a really important word, to verify. We want to show that it is true. This is a solution. But we have to remember, what does it mean for it to be a solution? For it to be a solution, that point has to be common to both equations. Right? So we need to have the point common to both equations. So we need to check that, see if that works. So let's start with the first one. We have y is equal to x plus 3 all squared minus 2. And remember, this is our point, and x is -4. Now, I am not using an equals because we're verifying. I don't really know if it's equal to until the end. So what I tend to do is I am treating this equation as a left-hand side and a right-hand side. So this is the left-hand side. This is the right-hand side. And then at the end, we'll be able to determine if it is equal or not. So we said that x is -4. When x is -4, I get -1 squared minus 2. 1 minus 2, -1. And guess what y was? Y was -1. So are those equal? Yes. Is it a solution? I don't know yet, because it has to be common to both equations. So we have to do the same thing with the other. So here's our second equation. At the end, we want to know that y is equal to -1 if x is -4. So let's put -4 in for x, and we will do that substitution and simplify. So -2 onto -1 squared plus 1, that's -2 times 1 plus 1, -2 plus 1, -1, and y was -1. So we have verified that these are correct, or that this point is a solution to the system. Okay, so let's look at part B. Part B asks, is this the only solution? So we know that one solution was -4, -1. Is there another solution? Well, there's a couple of ways in which we could do this. So whenever I'm looking at some of these, it's always great to have a picture in your mind. It could be a sketch. What's it looking at? What's it going to look like? It's almost like doing an estimation beforehand to have that picture. So you don't have to jump right to the algebra. So because these are in vertex form, I'm just going to do a really quick little graph. And so I'm going to graph this one with black. So my vertex is at -3, -2, right here. This is a parabola that opens up. So I have something like that. This other one, let's do with red. And so it has a vertex at -3, +1. Maybe about there. And it opens down. It's narrow. That picture alone gives us the answer. Is -4, -1 the only solution? No, it's not. And if we drew it carefully enough, we could be able to tell with our axis of symmetry what the other point would be. So I'm thinking that it's probably at -2, -1, just based on that information that we are given. Okay, and axis of symmetry. So if we had this point here, and we're saying that that is -4, -1, and our vertex was at -3, then this point should be at -2, -1. And that's a rough sketch, but all we need to know is there just the one point of intersection? And our answer is no, there are two. Why? Based on our graph. Now, some of you like to base this on algebra. So let's base it on some algebra. And this gets a little bit more cumbersome. But what's it mean to solve? We're going to put these two equal to each other. So we have those y's equal to each other, so we can do that substitution. I can substitute this value in for this y. So it's x plus 3 squared minus 2 is equal to -2 onto x plus 3 squared plus 1. And when I expand this binomial at squared, I get x squared plus 6x plus 9 minus 2 is equal to -2 onto x squared plus 6x plus 9 plus 1. So this gives me x squared plus 6x plus 7 is equal to -2x squared minus 12x minus 18 plus 1. If we do all of this out and simplify, we get 3x squared plus 18x plus 24 equals 0. 3 is a common factor, so I get x squared plus 6x plus 8 equals 0. So I have the factors x plus 2 and x plus 4. Something happened there. It's been down too far. Okay, which gives me that x is equal to -2 or x equals -4. But I don't have the y value, so what do we have to do? We would have to substitute these values, each of these values into the equation, one of the equations, and find out what we have. We already know that this one here gives me y is equal to -1. We already know that one. So let's continue with this. I need a new page, so let me do that. No. I'm going to capture this and make it smaller. Just to give us some room so it's still there. Okay, so we're looking at this particular one right here. So if x is -2, so I'm going to go with y is equal to x plus 3 squared minus 2. And what happens if x is -2? -2 plus 3 is 1. 1 squared is 1 minus 2, so y is -1. So we also know that. So our 2 points of intersection, okay, therefore, -2, -1, and -4, -1 are the solutions. So I've shown you a couple of different ways. Let's go back. We showed you just by graphing a sketch. It wasn't even a detailed graph. We said, oh, there has to be two solutions. Using the information that we know about our axis of symmetry and our vertex, and I had one point of intersection, and it's symmetrical, I could find the other point of intersection at -2, -1. And then I also said, well, you know what, we could also do this algebraically, and it has a lot of math to it, but we can also see that we have those two solutions. What's our third question? The third question says, okay, we have a quadratic-quadratic. So we know that we have two parabolas. What are the possible types of solutions? What could it look like? So I'm going to challenge you. There are four, right? Generically, four different types. So I'm going to challenge you to see if you can come up with what the four solutions could be. Now we've seen one similar to this already, just a little bit different, but if I had a parabola that opened up, like this one, and I had a parabola that opened down, like this green one, will they ever meet anywhere? No. So my answer to this one is no solution. So one thing that could happen is that there is one point of solution. The next one I'm going to draw, we've seen so we know it's exactly the same. Just translate it, and I'm just going to translate it horizontally just to show it in a different color. So there we have two parabolas. What do we have here? We have one point in common, so this is a one solution. We just had one that when I sketched it, we had a parabola that looked like this. We had a parabola that looked like this. And we said our answer was two solutions. There's one more that we haven't looked at. So I have this parabola. And then I have a parabola that is the exact clone and right on top of it. Right? I can show you that this one's a different one. Oops, it moved. I'll just continue here. So we have this parabola here on the right, the furthest one on the right. It's the exact same parabola. It's a clone, and they're right on top of each other. They're the exact same place. What is the solution to that system? What point or points do they have in common? Well, they have every point in common. So this is infinitely many solutions. Very similar to what we've seen in grade 10. Okay, and then our symbol for infinite. We can use that symbol. So these are the four possibilities when we're looking at solutions. Let's look at another example. Example 5 is putting some of this in context for us. So in a circus stunt, two clowns are lunged towards each other from two slightly offset levers. That's so that you know they're not gonna like head first into each other. The first clown's height is modeled by this function. And the second clown's path is modeled by this other function. Now, h of t is the function of height with respect to time, and that's the height in meters and time in seconds. In the routine, the clowns high-five each other. What's the solution to the system? What does it represent? So just a little schematic of what this might look like. So we have a graph. So we have this clown coming this way. We have this clown coming this way. So it would look something like this. Okay. Here are the equations algebraically. We have an idea from our graph that they're hitting in one point. And from the context, we knew that. This is set up nicely for elimination. So what I'm going to do is I'm really wanting to eliminate the t squared. If possible, it's always nice to eliminate, but you have to also eliminate your y value. So remembering that h of t is like our y value. So I'm going to change this sign, change this one, and this one. Remember, it's like multiplying that equation by -1. So every term's sign must change. And h of t, subtract h of t is 0. Negative 4.9 t squared plus 4.9 t squared, that gives me 0. So I have 13.7 subtract 24.5, that gives me negative 10.8 t. And 0.4 add 25 is 25.4. Right, so if I do this, I get 10.8 t is equal to 25.4. T is equal to approximately 2.35. What does that mean? Do I need to know now the h of t? Well, we can find out h of t. So you put h of t into one of the equations, and that's going to give us that value. All right, so, well, we can do that. Let's do the top one. H of t is equal to negative 4.9 t squared plus 13.7 t plus 0.4. Running out of room. And we're looking for h of 2.35. So wherever there's a t, you're going to put that value in. So we have negative 4.9 to 2.35 squared. And I'm going to have to go plus 13.7 times 2.35 and add 0.4. So you have to do the math out. I'm just going to pause while I get out my calculator. I did the calculations off air here. So I did 2.35 squared and got approximately 5.5225. And I multiplied that by negative 4.9 and got negative 27.06. 13.7 times 2.35 to get 32.195, and then adding in the 0.4, I get 32.595. Subtracting 27.06 give me 5.535. We're close, right? Because there is some rounding here. So my ordered pair that I have is 2.35 and 5.535. What does that tell us? Right, if we go back to what that original question was asking, what is that solution? But what does it represent? Well, this is representing time. This is representing height. But together, the solution is where these two clowns high-five each other. So it represents where they high-five each other. This occurs 2.35 seconds into the routine, and they are 5.535 meters above ground. So it's putting it into context and being able to solve. Here are some questions that I've picked from section 8.1 and 8.2. I recommend that you do for homework and practice so you understand and get the feel of how to do these questions.